this question, work problem number 3 then. Newton's law of cooling. Here it is. The temperature at a given time, theta t, equals the initial temperature, theta 0, e to the minus kt. So it's time dependent. So the function could be written theta, that's a function of time, theta t, equals the original temperature, theta 0, e times e to the minus kt. And this bit is a classic exponential decay function. Minus means it's decaying, so it's an exponential decay, and you can see it here. Okay? And from the physics point of view, and from the engineering point of view, an exponential decay like this with the base e is applied to something where the rate of change of something depends on how much there is. And this is a measure of the excess temperature above, say, room temperature rather. So we are 16 degrees above room 0 at the start, and that's indicated here, look, 16 on the graph. So at time 0 here, the temperature is 16 degrees, and then it starts to cool. And the rate at which it cools depends on how far above room temperature it is. You can imagine, you would expect, common sense would tell you, that as you approached room temperature, the rate of cooling would reduce, wouldn't it, until you sort of approach room temperature and it levels off at room temperature. So the further you are above room temperature, when you start to cool down, the greater you'd expect, the greater the rate of cooling would be. And that's a classic exponential change. So that's why the function looks like that. Whoa. That's why the function looks like that. So that's the first thing I want to point out. If we look at this function, theta 0 means the temperature at 0. And as I've already pointed out, that's this point. So if you ever want to sketch an exponential graph, that's always where it cuts the y-axis. What we're after in this temperature, in this question rather, is we want to determine the rate of change of temperature after 40 seconds. So at 40 seconds, which is here, we want to know the rate of change of temperature. What is it about that curve that tells us the rate of change? The gradient. Okay? The gradient. Okay? So look, the gradient is getting less. Steeper gradient there, less steep gradient there. The rate of change of temperature is reducing. And we want to find out what that is. So as soon as I see, determine the rate of change of temperature, what's that telling me to do? Differentiate it, yeah. So I've got the original function, theta, which is a function of time, equals theta 0 e to the minus kt. Or actually, in this particular case, putting the values in, theta t equals 16 e to the minus 0.03 t. So we've got some values and we can put them in. T is time. When time is 0, we know that the temperature difference is 16. So this t is in there because this is a function of time. All it's saying at the start is that at the start the temperature is 16. So when t equals 0, it's 16. But then time's going by, and this is how it changes. Okay? So that's the function. So, as Tom suggests, we've got to differentiate this now, and then find out what that rate of change is when the time is 40 degrees, at 40 seconds rather. So substitute in 40 for the time and work it out. I'll just pause, see if you can finish the question off. So first step, theta prime equals 16 times minus 0.03. 16 times 3 is 48, so minus 0.48 e to the minus 0.03t. So Alex, we don't change the power because it's an exponential function. It stays the same, doesn't it, in an exponential function? Yeah. So now we've got the theta prime function, or the differential function, we can find the rate of change of temperature with time when the temperature is 40 seconds. So theta prime turns out to be negative 0.14 degrees centigrade per second, okay, to 3 significant figures.